Okay. So last time we introduced well, we didn't really introduce quantum mechanics. We just talked about three concepts: reflection, emission, and absorption. So we left off talking about emission, I believe. Do you remember what the difference is between, like, if you had to describe it to like a young kid, what would you say is a big difference between reflection and, for instance, absorption in terms of what the electrons do? Anybody want to take a stab at that? Okay, so like in one of those two, the electrons would jump to another level, a higher level, right? Whereas in the other one, you could describe it as the electrons would oscillate, but they wouldn't jump to another level. So which one would be reflection and which one would be absorption? Kristen, I'm gonna pick on you. Okay, let's see. Yeah, very good. So, yeah, thank you, Kristen. So she says the just making the electrons oscillate, that would be what reflection would do. Whereas if the electrons capture the energy and they jump to a higher level, that would be absorption. And then obviously emission is just the opposite of that. When the electrons come back down, they release the energy. Now, at some point, we'll actually do the calculations in terms of predicting what kind of colors actually come out when electrons fall back down. We'll do that, but we'll do that later on, not today. Okay. So we left off talking about emission. Now, I didn't answer these questions, but you probably know this from some space science that you might have done, that there is a connection between color and temperature, right? I think you do this in grade 9, if I remember correctly. So I want to actually talk a little bit about tying these two questions in with blackbody and blackbody radiation. Okay. So one of the sims that you have to look at is the same with blackbody radiation. This is something that Max Planck was investigating. Now, that name should ring a bell because that name came up in the E equals mc squared video. Remember, he's the one who gave, I guess you can say, gave Einstein his break. And he was absorbing, if I remember correctly, I think he was asked to look at efficiency of incandescent lights to see if they can make them more efficient. So he was studying how things absorb energy and give off energy. So let me explain actually what a black body is. So a black body is something that is really, really, really good at absorbing lots of different types of radiation. So it's a really, really, really good absorber, but it's also a good emitter. Okay. It actually has to be both. And you'll notice that something highlighted in green that says a good absorber has to be a good emitter. And because otherwise it would actually violate something that you learned way back, probably in elementary school. It has to do with the laws of thermodynamics, specifically the second law, which we can basically describe it as heat transfer. So you know that hot things will give off energy, and eventually over time they'll cool down, and things that are colder will pick up that thermal energy and heat up, right? Now, why does a black body need to be both a good absorber and a good emitter? It's because we can do like a thought experiment to show why it would need to be both good at absorbing and good at emitting. Okay, so imagine a room. Okay, so here's my room. It's a closed system, and inside there's my black body, which could be, I don't know, maybe Well, here they have, for example, like a lump. I think this is like a lump of coal as an example of a black body. Black body, even an oven could be considered like a black body. But whatever. Imagine this is a black body, but it's good at absorbing, but it's not good at emitting. Okay. And beside that is, let's say, a cup of coffee. Well, that's not a good color to pick. Let's try a different color. Let's try red. Okay, so here's my cup of coffee, okay? Now, imagine that the coffee is really hot. No, actually, sorry, let's imagine that, imagine the coffee is really, really hot. Okay, so what's gonna happen is, we know the heat will be transferred from the hot object to the cold object. So imagine that my black body radiator or black body is really good at absorbing, okay? So what it would do is it would absorb heat from my coffee. I can imagine like there's lots of cups of coffee in this room that are giving off heat. Now, what would happen is you would expect eventually that the temperature of the black body and the coffee would reach thermal equilibrium. So they'd be basically the same temperature, right? But if our thought experiment was to show why the black body has to be also a good emitter, imagine this. Imagine it was good at absorbing but not good at emitting. So what would happen then is the black body would keep stealing energy, thermal energy from the coffee. And that means the coffee would keep getting colder and colder and colder. Eventually, maybe even, I don't know about absolute zero, but it would get colder than the black body, which doesn't make any sense. Because what's supposed to happen is if the black body gets hotter than the coffee, it's supposed to emit that radiation back, so they're both in thermal equilibrium. So it has to be good at both. Otherwise, it would literally suck up all the thermal energy in the room. It would be really hot, and the rest of the room would be really cold. And that doesn't make any sense because it's not our everyday experience. So a black body's got to be really, really good at both. Now, if you Google like stars, it's a bit controversial whether or not they're considered ideal black bodies. So most sites will consider them black bodies. I'm not really, I guess we'll go with they're mostly right. So the idea is that, what's a star? Star is something that's giving off lots of heat, lots of radiation, right? And like a light bulb is kind of similar to that, right? A light bulb, as it heats up, is giving off electromagnetic radiation. Now, Max Planck wasn't studying stars, he was studying light bulbs. And he was specifically trying to understand the relationship between temperature and what kinds of EM radiation was being given off. I think you probably noticed that incandescent light bulbs, they're not very efficient. There's a lot of wasteful energy. I'm actually, what's really funny though is I might be, girls, you know what an incandescent light bulb is, right? Anyone know what an incandescent light bulb is? Because I'm saying this, I'm thinking to myself, I am a lot older than these kids. I grew up with incandescent light bulbs. Maybe these kids don't know what an incandescent light bulb is. Do you girls know what that is? Rebecca, do you know what it is? Yeah, go ahead.
I've heard of it, but like I don't really know exactly what it is. So
yeah, see, that's part of my problem is that I'm assuming it's like when I make references to. I remember one time I said, "You sound to a student, you sound like a broken record." You know what the student said to me? You ever heard of that reference? You sound like a broken record.
Yeah.
Do you know what it means?
We weren't born last year. You know what that means.
Well, I don't know. That kid said to me, "What's a record?" That's what she said. So an incandescent. I know, it's sad, eh?
Oh no, I was gonna say.
Sorry.
No, I'm sorry. I was gonna say last year at camp, a kid asked me what the Macarena was, and I almost cried.
Oh, so you're old. So an incandescent light bulb has a filament. I don't know if you could see. So you see that there's a filament right here. Actually, I could probably draw on this. So, right, see this? This is a filament. So the way it works is electricity flows through this wire. Not really sure which direction it's going, and this wire is very thin. So there's a lot of resistance. And what happens is, you know, with resistance comes heat. And with a lot of heat comes light. This is how an incandescent light bulb works. But there's a lot of heat, and that's the problem with incandescent light bulbs. Whereas if you touch like so if you touch an incandescent light bulb and it's been on for a while, like you will burn your hand. Like that's how hot they get. Whereas an LED light, they work very differently. So they don't produce a lot of heat. That's why they're so much more efficient. There's not a lot of wasteful energy. But this is going back to late 1800s, early 1900s. You know, we had no idea about LEDs. So Planck was studying the photo. Oh, sorry. Yeah, I didn't want to talk about entropy, but you're absolutely right. Entropy always increases. Second law of thermodynamics. Thank you. So Max Planck was studying, like I said, incandescent light bulbs, trying to figure out how to make them more efficient. I think that's, if I recall that correctly, that's what he was doing. So look, we can kind of model that with this sim, right? In terms of what is given off as something gets heated. So for example, right now, if we look at the Earth, it looks like it's giving off a little bit of maybe, I don't know if you can really see much here, but I would imagine it's probably giving off a little bit of infrared radiation. The Earth doesn't give off any visible light because it's just not hot enough to do that. But you can see what happens as we start heating this up. As we start to heat this up, we can see that we start producing heat. See if I can zoom in here. Okay, we start producing some heat. You can see the graph now is starting to lift a little bit. And if we keep heating this up, it gets a little bit hotter. Now we can start seeing some visible light. So if I look at my graph, you'll notice there's a lot. If I look at the area under the graph, there's most of that area is, I should mention, to the right of my graph is infrared radiation. To the left, to the right of my BGR barcode here, which represents visible light. To the right of that is infrared. To the left of that is UV radiation, okay? You'll notice that it's mostly heat. Again, Planck was studying light bulbs, and the reason why, if I remember correctly, is because they're not very efficient. So most of the heat is actually, most of the energy that's given off is actually heat energy. Now, but there is visible light when it gets hot enough. And if we go to the sun, so if we heat this up more, you could see, obviously there's a lot of heat energy. You can see there's a lot of visible light, and there's also UV radiation, which makes sense. We know that, right? We can get sunburn because of UV radiation coming from the sun. So Planck was studying the effects of temperature and basically types of electromagnetic radiation that was coming out of an object, right? This black body, for instance. Now, if we keep heating it up, which I can't see now, my graph just disappears. The idea was that, well, the thinking of the day was that there would be a pattern that is followed, which looks like this. So the pattern was believed to follow, hold on, let's get my pen here, this curve. All right. In other words, eventually, if something got hot enough, the idea would be they would just keep drifting to the left, and eventually it would shift all the way into the UV spectrum, which I guess if you go back to this question, the second question, would a star become invisible if it continued to heat up? So if that pattern was true, and all the radiation shifted to the UV spectrum, which it doesn't, but if it did, then I guess you could technically say the star would become invisible to us because we can't see UV radiation, right? But that's not what happens. Oh, I skipped over this question. Why is the sun yellow? So the sun is yellow because if you look at the, we go back to this temperature of the sun. Let me zoom out. Let me zoom back in, I guess. Most of the visible light is actually in the yellow range. So if you were to keep heating it up, you would see that it would actually shift, which you can't actually see too well here. But there is a connection between temperature and star's color. That's really hard to see here. If it got hotter, it would become white or blue, depending on how hot it gets. So it actually would shift to the blue end. So that is what happened if the sun got hotter. It would actually switch from yellow to white or blue, depending on the temperature. But would it become invisible? No, obviously we know it won't become invisible. Where's my thing? Okay, it's right here. Okay, it would not become invisible because what happened was when Max Planck was actually studying this, it didn't follow this pattern. It didn't follow that pattern at all. In fact, it followed the pattern that we just looked at. It went up and then it dropped off. So it didn't just keep going up like this. It actually dropped off. In fact, there was a name for what was observed called the UV catastrophe, because it was predicted that the radiation would shift to the UV side, but that's not what happened. So that left scientists scratching their head. So to me, this kind of reminds me of what happened with Michelson and Morley. You know, you have you're investigating something, you make a model or a prediction, you come up with an experiment. The experiment gives you vastly different results. So then either you made an experimental error or errors, or your model is completely wrong. So obviously the model is completely, well, in this case, the model was completely wrong. There was nothing wrong with the experiment. It was the actual model that was wrong. So Planck had to come up with an explanation for what he saw. Like, why did all of a sudden, you know, why did it just drop? Why did the radiation just drop off like that in the UV range? And he came up with a really, really wild idea. Okay. And his wild idea was this. He said that, well, maybe we just cannot make any amounts of energy. Maybe there's only certain amounts or packets of energy that we could produce. And he called these packets of energy quanta. Because the original idea was that if you heat something up, it gets hotter and hotter and hotter, you just start producing shorter and shorter wavelengths of light, which we know shorter wavelengths means more energy. So the idea was you can probably produce any range of energy values, but that's not what the model is showing. So he said, maybe it's not just any possibility, maybe it's specific amounts of energy called quanta, which, by the way, if you think of the term quantum mechanics, this is like the beginnings of this idea where values are quantized. Now, I want to actually talk a little bit about what that means. Because when Planck came up with this idea, it actually bothered him. He came up with the idea, but he had a hard time with it. I think I wrote it somewhere here, which is right here. So he said that the energy that is emitted is quantized, can't just be any amount, has to be some multiples of a minimum value. And he actually struggled with this idea. He had a hard time with it. Now, okay, so think about your everyday experience, right? Where would you see examples of quantization in everyday experience? So let me give you a visual by what I mean by this. So think of quantization as this: steps. You can be here, you can be here, you can be here, but you can't be in between the steps. Now, you know, we talked about this with the atom. This is actually how the atom works, right? We actually already talked about this when we talked about glass. You know, why is it that glass is transparent? It's because there's not enough energy to make the electron jump. So that means they're not getting the minimum amount, the quanta of energy to jump up a level. But where do you actually, like, where do you see this in your everyday life? Does anyone have any experience with quantized values in their everyday life? It's actually hard to think of one. I mean, okay, I guess maybe we can say, well, people are quantized. You can't have half a person. I guess that's true, right? You can't have half an organism. I guess that's true. But like, you know, you fill up a glass of water, you talk about changes in temperature. You know, these aren't quantized values. Your food, the amount of food you put on your plate, is that quantized? Not really. It doesn't seem like it is, right? We don't think of the world around us as it being quantized. So this is a very, very strange idea when to Max Planck himself, even though he came up with this idea. Any questions about this? About what I mean by like everyday experience, you don't really see this. Anybody want to add something to this? Okay, so this equation here, this is the equation that Max Planck derived to show the minimum amount of energy. So this is an equation that basically, so n is a whole number, so multiple, like 1, 2, 3, 4, 5. F is the frequency of your light, and h is Planck's constant, which is a very, 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 very tiny number. And because it's so tiny that we, who are really large organisms, we don't see quantized world. We don't notice that because Planck's constant is just so darn small, right? But I guess if we were like electrons or atoms, we would see quantized. We would see a quantized world. We would see the world very, very different. All right, so we could use Planck's equation to answer some very simple questions about energy. For example, we could look at an ultraviolet photon, and we can figure out how much energy it has using this equation. Imagine we're dealing with one photon, so we're going to say n is just 1. How much energy would be in a photon of light that has a frequency of 1 times 10 to the 15 hertz? So the equation predicts that the amount of energy from a photon, a UV photon that has a frequency of 1 times 10 to the 15, would be Planck's constant. Now, the unit is joules seconds times the frequency. That's 10 to the 15 hertz. Now, remember what a hertz is? A hertz is the same as per second because it cycles per second. So you can say that the unit of frequency is 1 over s, right? It's per second. So you'll notice that these would cancel out, and you'll be left with simply joules. So the energy from one UV photon at this frequency would be 6.63 times 10 to the minus 19 joules. Okay. So one photon would have that much energy. Then you can think about 2 photons or 3 photons or 4 photons or multiples of this. But you can't have 1.5 of it. You can't have, because you can't have half a photon. Now, we have a follow-up question here. What's the energy in electron volts for a blue photon of light with a wavelength of 460 nanometers? So the equation is E equals HF. Now, if we don't have frequency, if we have the wavelength, we know V equals F lambda. So F is V over lambda, but F is actually the speed of light, so we can just say it's C. So we can plug that into this equation and say E equals H times C over wavelength. That would be Planck's constant times the speed of light over the wavelength. So if we do that, where's my calculator? 6.63 to the exponent 34 negative times 3 to the exponent 8 divided by 460 to the exponent negative 9, because a nanometer is negative 9, 4.3 times 10 to the minus 19. Now, it says to equate that in electron volts. If you remember, an electron volt is 1.6 times 10 to the minus, whoop, look out, minus 19 joules. Okay, so in terms of how many electron volts this would be 4.3 times 10 to the minus 19 over 1.6 times 10 to the minus 19. So basically 4.3 over 1.6. So that would be about 2.7 electron volts. So this would be about 2.7 electron volts. Any questions about what it means to be quantized and how to use Planck's constant in determining the energy of a photon? We okay? So this is going to come up a lot. Planck's constant is a really, really important concept in this whole unit. So you're going to see it quite a bit. And calculating energy of photons, obviously another really, really important topic. Okay, now we can expand on this idea to look at another really important, I guess you can still call it like a bit of a head scratcher, the photoelectric effect. Now, you know the answer to this question. If I say to you, is light a wave or a particle? What's the answer? Don't be shy. What's the answer? Is it a wave or a particle? So last year we talked about light. I think we didn't talk about it as a particle, but we obviously talked about it as a wave because it does things that waves do. For example, it interferes, right? We talk about superposition of light. So obviously it's a wave, but I want to remind you about properties of waves. Last year we talked about certain properties of waves. One was intensity. Okay, So 1 was intensity. So I'm going to pick on Tavine. Tavine, let's visualize a sound wave, okay? What would the intensity of a sound wave, like what would it be? What would you measure it as? So remember, okay, how about this? Let's back up a little bit. Yeah, my wave particle duality. So last year Maya mentioned that it's both a wave and a particle. That's where we're going to get to, okay? So last year we talked about light as a wave. Now, if you remember, we talked about certain properties of waves. Intensity is one. Like for example, remember we visualized what a wave looks like in a spring. We talked about, for instance, like how you calculate the energy of a wave. So the energy of the wave would be like its amplitude. So how do you, how would you manifest that in terms of like a wave? So for sound, you could say, well, the energy would be a measurement of how loud it is. But for light is funny. Light, you would think that if it's brighter, it would have more energy, but it doesn't work that way. In fact, the photoelectric effect is something that Einstein was investigating. It's actually one of the papers that he wrote. Remember, he wrote like 5 papers, and I said that we would talk about one of them. This is the one. This is the paper on the photoelectric effect. I want to show you the photoelectric effect, because this is one of those things that you're going to have to look at. Yeah, that's right. So look, if I take light and I shine it on metal, the light might have enough energy to dislodge the electrons from the metal. And then you can measure the electrons jumping across, which would be the flow of electrons. That would be electricity, right? So for example, if I take this light and I turn it on, you'll notice that as I turn on the light, I get electrons that are being dislodged from the metal, right? And they're jumping across. Now, what you'll notice is that they're not all moving at the same rate. Some have more energy, some have less energy, right? So we can say that the kinetic energy of the electrons, the faster ones obviously would have more kinetic energy, the slower ones would have less kinetic energy. What's really interesting is when I play around with the intensity. So what does the intensity do? Well, the intensity is a measurement of the amount of light. Now, what it does is you'll notice that when I have more intense light, I get more particles, right? I can see that. So if I drop the intensity, there's a certain point where if there's not any light, so right now there's a little bit of light, there's no light at all, there's no electrons being ejected, right? So if I have a certain amount of light, you'll notice that, okay, I see electrons are getting ejected. Some fast, some moving slower. If I make it brighter, I see there's more electrons. But they're not getting any faster though. You notice that? I'm getting more of them, but I'm not making them faster. In fact, if I can put up a graph here, which might be a little bit hard for you to see, where if I play around with the intensity, nothing happens on the graph. Okay, now watch what happens though when I change the frequency. So right now, let's start off with the red end, okay? So we know red end is longer wavelength, less energy. So you'll notice that, okay, so lights are off. I make the light bright. You're in a lot of red light. It actually might be infrared light. Nothing's coming out. Notice that? Nothing's coming out. Okay. Now, as I move towards shorter wavelengths, so right now I'm in the red, so I'm starting to go to the yellow. Still nothing, right? Okay. Start to go to the greens. Okay, so here we go. So now right now we're shining green light, and you'll notice they're coming out kind of slowly. So the kinetic energy of these electrons would be some value. That obviously is a function of their mass and their speed, right? Okay. Now, watch what happens when we decrease the intensity. You'll notice that the speed doesn't change, right? So I can play around with the intensity, and all it does is it changes the amount of light, but not the speed at which the amount of electrons, but not the speed at which the electrons come out. Now, watch what happens. I'm gonna make it as bright as possible. When I start moving down to the blues, you'll notice now I'm getting electrons that are coming out faster. Now, some are still coming out slow. They all come at the same speed? They don't actually all come at the same speed. It looks like they are. If I keep going down, you'll notice the electrons are coming out even faster. So what's going on here? Because it seems like the color of light is having an effect on the speed of the electrons, but not the intensity of the light. So there's obviously something bizarre going on. Okay. So Einstein looked at these results. He thought about what Planck came up with and the idea that energy is quantized, and he came up with a really, really great idea. He said this. He said, think of light as a particle that has a certain amount of energy. All right. This is based obviously on Planck's idea where energy is quantized. So these photons represent a bundle of energy that is a function. The amount of energy they have is a function of their frequency. Has nothing to do with the intensity. It's a function of the frequency of the light. So in other words, he's building on Planck's idea to explain the photoelectric effect. It's not because, in this case, light is a wave. It's because the different photons of light at different frequencies have different amounts of energy. And if they have the right amount of energy, they can eject the electron. If they have more energy, they can maybe eject the electron with greater speed. That's why you're seeing the effect of frequency and the speed. There's a correlation there. Does that make sense to you girls? So do you see how that sim is tied together with Planck's idea and his equation, E equals HF, where the higher the frequency, the more energy the photons have, which means when they eject the electrons come out with greater speed. Are we okay with that idea? Okay, so then why don't we just do these last two equations and we'll call it, all right? So we can actually work out how fast these electrons are moving, or we can work out the energy of the light in an equation that looks like this. Now this equation, you can see HF, so again building on Planck's idea, where energy is quantized, right? Planck's constant times the frequency of light. So what does this equation say? This equation is saying that the kinetic energy of an electron is a function of the energy of the photon minus something called the work function. Now, the work function is the energy required to get that electron off the metal. You can think of it like the ionization energy. Okay. Sorry, it's not. No, it's not the ionization energy. No, sorry, it's not the ionization energy because the electrons are freely moving. So it's not. I think it's different than that. So this is the energy required to get the electron off the metal. Okay. So obviously, if there's a difference in energy, then that energy would go into kinetic energy. So for example, we could use this to answer a question like this. What would be the minimum frequency of a photon required to eject an electron if the work function is 3 electron volts? Minimum energy means, or minimum frequency means that the electron would escape the metal with no speed. Okay, that's what it means, no speed. So the kinetic energy would be 0. In that case, HF minus W would have to equal 0. So we could say that W equals HF. So the work function is the minimum energy required to strip the electron. That says it's 3 electron volts. So that would be 3 times 1.6 times 10 to the minus 19 joules, because an electron volt is 1.6 times 10 to the negative 19 joules, is equal to Planck's constant times F. So obviously, we're going to divide this energy by Planck's constant. And we'll get the frequency. Oh, sorry, Planck's, that's the wrong value, minus 34. So the frequency of light. Yeah, it should be minus 34. So that would be 3. What was the work function again? Okay. So that's 3 times 1.6. So that would be 4.8 to the exponent negative 19 divided by Planck's constant. So the frequency would be about 7.2 times 10 to the 3, 6, 9, 12, 14. 7.2 times 10 to the 14 hertz. I'm not sure exactly what color that would be. So if a UV photon is 10 to the 15, and this is 7 times 10 to the 4, it's close. This probably would be a blue photon if I had to guess. I would imagine it's probably either still a UV photon or a blue photon. Now you can look it up. There's obviously charts you can look up to see what color is required. But that would be the minimum energy. If it's hit with a photon that has more energy, then the difference would go into the kinetic energy of the electron, which you should know how to calculate because that's just simply a law of conservation of energy equation. Okay, we'll do one more. So you can see how the photoelectric effect is directly tied to Planck's idea. So we do one more question. What would the speed of the electron be if ejected by a photon of light where we have the wavelength and the work function is 1.95 electron volts? So in that case, there is obviously going to be leftover energy. So we could say the kinetic energy is HF minus the work function. Now, remember we said if you don't have the frequency, you can do C over lambda. So that would be Planck's constant times the speed of light over the wavelength minus 1.95 times 1.6 times 10 to the minus 19 joules. So this is going to be in joules too. Okay, so Planck's constant times the speed of light. Oops, what happened there? Sorry. Times the speed of, did it not clear? Sorry, something doesn't clear it. All right, divided by, what was the wavelength? The wavelength was 3 times 10 to the minus 7. So 6.6 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 13, 14, 16, 17, 18, 19. Negative 19. So this is 6.63 times 10 to the minus 19 joules minus the work function. That's 3.12. So that would give us approximately 3.5 times 10 to the minus 19 joules. And then we subtract them. So we can just simply plug that in now to our kinetic energy equation. Let's get that over. And say kinetic energy, so we know V squared would then be 2 times this value over the mass of the electron, which I think is, it's 9.1 times 10 to the, is it minus 31? Sorry. Mass of electron. Yes. Okay. Okay, and then we can just take the square root of that. So that would give us a speed. So what do we say? 3.5 to the exponent 19 times 2 divided by 9.1 to the exponent 31. So 8.8 times 10 to the 5, which is a reasonable answer. Okay. All right. Then what we'll do on Thursday, and this is something that Maya mentioned, is it a week ago? Talking about how, Maya, you remember you were mentioning something about light, even though it's considered massless, it has momentum. Was that you that mentioned that?
Yes.
Okay, so that's actually, we'll talk about that Thursday. I did want to draw your attention to a neat video clip I came across. So I put it in I updated the file and I put it in there. It's a video from 60 Symbol to talk about the uncertainty principle. So can you watch that video and then we'll talk about it on Thursday, because it's actually pretty interesting. Anyway, so next time we get together, we'll talk about how we can use the idea of E equals hf and E equals mt squared and talk about the momentum of a photon. Okay, girls? So let me stop recording and take any questions.